Okay, I'm going to use this PhET simulator to replicate a demonstration I would do for you in class after talking about series circuits, or maybe even before. So I have a series circuit with two bulbs in series, a 10 ohm bulb and a 40 ohm bulb. I'm using two batteries in series with one another to boost my EMF to 18 volts, but that's not really relevant, and I have a switch here. And I want to point out something that maybe didn't do before, is that when the switch is open, notice that its resistance is essentially infinite because we have an air gap there, and air is a very poor conductor, so its resistance is essentially infinite. So that's important to know in certain situations. An open switch has infinite resistance, whereas a closed switch has essentially zero resistance. Okay, but that's not the main point of this. So what I want you to do is I want you to predict which bulb will be brighter or possibly the same when I close the switch. Okay, so I want you to work that out. Okay, so hopefully you've thought this through, maybe you've done some math. So let me point out a few things about the two bulbs in isolation. I have the 10 ohm and I have the 40 ohm. So when the manufacturer made these bulbs, the idea is that different resistance will give different brightnesses, different power. And so how we'd figure out the power for each one would be V squared over R, because they're assuming they'll be plugged into the same voltage source. That's why they have the tiny little bases the way they do, so you can't accidentally put them in a regular light socket. So if we know P equals V squared over R, then we can see that P is proportional to 1 over R. So the lower the resistance, the greater the current. Or excuse me, the greater current, true, and greater the power. And we saw that in an earlier lab. So we would expect that the 10 ohm bulb would have 4 times the brightness, or 4 times the power as the previous one. So let's switch back over to our previous circuit. Okay, and so let's see, does this situation apply? We again have our 10 ohm and our 40 ohm. So would we expect the 10 ohm to be brighter? Well, according to the other analysis, yes. All right, so let's turn it on. Let's see what we get. Okay, so if you can't tell, these yellow lines radiating from give the relative brightness. We see that the 40 ohm is much brighter. Okay, so how do we resolve that? That completely contradicts what we learned about a light bulb. If I were to plug this light bulb into by itself, it would be much dimmer than the 10 ohm. However, when I place them in series, it flips. It's almost by magic. So that's the important rule or concept I want you to get here, is when you put two or more bulbs in series, the highest resistance will always be brighter, whereas if you put them in individual circuits, the lower resistance will always be brighter. So how do we resolve that? All right, so this is where your understanding of series circuits and the notes really is helpful. Okay. All right, sorry about that glitch. So let me just draw a schematic of the two bulbs without the battery. I don't need that. So there's our 10 ohm bulb. We're just going to use this as our symbol for it. And here's our 40 ohm bulb. So why is this, and maybe you've already figured this out. Okay, what changes when we put things in series? Well, the hallmark in my mind of a series circuit is the current is the same everywhere. So the current coming out of the battery, which I call IC, must be the same as the current going through the 10 ohm, which must be the same current going through the 40 ohm. And that's not what happens when you put them in individual circuits. The current will be different for individual circuits. So the series circuit, they must be the same to follow the junction rule or the law of conservation of charge. If you were to say this should be this should be brighter because it has lower resistance, you're assuming they have the same voltage. And when we mean voltage, we don't mean the voltage source, we mean the voltage drop. And they don't have the same voltage drop. Okay, the voltage drop across one is not going to be the same as the other, but we know they have to add up to the overall EMF. So the voltage drop across either one is I times R. Whoops. And if the currents must be the same, then that tells us the one with the bigger resistance must get the bigger voltage drop. And therefore, if we go to apply this equation, we see that that V squared part for the bigger resistance is going to offset the bigger resistance and give us more power. Now that's a little bit confusing, so let me go the easier route. The more relevant equation, or more directly relevant equation, is I squared R. So if we know the I's have to be the same because they're in series, then this tells us directly that a bigger resistance gives us bigger power. So that's the one situation where you can get more power with bigger resistance. So I just want to point that out because it's a counterintuitive example.